Hello everyone, today we will discuss about number systems, that is number systems in computer. We need number systems in order to communicate with the machines and the computers. So as we all know that computer cannot understand human language, that means it cannot understand words and letters. And even if we type something on the computer still displays it on the monitor. So you might wonder how it is that computer is able to interpret and display the exact letters of words that we press on the keyboard. That is possible because we are able to interact with the computer and the computer is able to understand us because of the number system. So each alphabets on the computer, uppercase and lowercase, along with all the symbols, exclamatory sign, question mark, comma, semicolon, colon, then decimal and other functional keys like alt, shift, space, and all have unique ASCII values. Now, which are then converted into the language, the only language that the computer can understand. That is the binary language, the language of zeros and one. So, for a computer, a 0 means off and 1 means on. So, a binary number system has only two numbers, that is your 0 and 1. Likewise, there are other number systems in computer. So there are total 4 types of number systems: binary, decimal, octal and hexadecimal. So today we will see how to convert numbers from each of those number systems to the numbers of other number systems. So let us begin with the most common and basic number system, that is our decimal number system. So the decimal number system is a base 10 number system having 10 digits. So base 10 number system means what? This number system will have 10 digits. So what are the 10 digits? Count 0. 0 is also a part of the number system. So 0 itself is also a number. So count from 0 to 9. 0, 1, 4, 5, 6, 7, 8, 9. So you will see total of 10 digits. And all the other numbers that we write in this number system, that is the normal number system that we use in our daily to daily life, all those numbers are composed of the numbers that are present from 0 to 9. Decimal number system is also a positional value system. This means the value of digits will depend on its position. Let us take an example. We have three numbers: 734, 971 and 207. The value of 7 in all three numbers is different. In 734, the value of 7 is hundreds. That is 7 into 10 to the power 2. In 971, it is 10. That is 7 into 10 to the power 1. And in 207, it is 7. That is units place. That is 7 into 10 to the power 0. Anything to the power 0 is 1. So 7 into 1 is 7. Here 7 into 10 is 70. That is 900 plus 70 plus 1. Here 7 into 10 to the power 2 means 100. 700. So 700 plus 30 plus 4. So each of the numbers in a number system has their own positional value. So the weightage of each position can be represented as follows: 10 to the power 0 for units place, 10 to the power 1 for tens place, 2 for hundreds place, 10 to the power 3 for thousands place, 10 to the power 4 for 10,000, 10 to the power 5 for lakh, and likewise. So in digital systems, instructions are given through electrical signals, and we know that variation is done by varying the voltage of the signal. So having 10 different voltages to implement decimal number system in digital equipment is difficult. If we want to work with electrical signals by varying the voltage of the signal, the most easiest way is to go with the binary system. That is the low voltage and the high voltage. So many number systems that are easier to implement digitally have been developed. So we will look at them in detail. In order to convert any base to decimal, the formula is the digit into the base. So this number is a system of base 10. Binary number is a system of base 2 to the power positional number. So the first position of a number, the position number, the first position is considered 0. Then the second position is considered 1. Then the third position is considered 2. Here we will count from 0. As you can see, 4 into 10 to the power 0 plus 3 into 10 to the power 1 plus 7 into 10 to the power 2. Calculate, you will find 734. So likewise, whenever we will try to convert from any base to decimal, we have to go through this formula. Now let us talk about binary number system. The easiest way to vary instructions to electric signals is two-stage system, on and off. On is represented as 1 and off as 0. Though 0 is not actually no signal, but signal at a lower voltage. Likewise, 1 is a signal at a higher voltage. The number system having just these two digits, 0 and 1, is called binary number system. Now, each binary digit is also called a bit. That means 0 is a bit, 1 is a bit. Now, binary number system is also positional value system, but here the values will be expressed in the powers of 2. In this system, the values were expressed in the powers of 10. Here, the values will be expressed in the powers of 2. So, the first value is 2 to the power 0, second 2 to the power 1, third 2 to the power 2, fourth 2 to the power 3, fifth 2 to the power 4, sixth 2 to the power 5, and so on. So, any decimal equivalent of the number is sum of the product of each digit with its positional value. Remember this formula. Now we will go through an example. Let us see. 11010 to the base 2. This is a binary number. Now we are going to convert it into a decimal number. So see, 1 into 2 plus this 1 into 2 plus 0 into 2 plus 1 into 2 plus 0 into 2. Now let us talk about the positional values as I have told earlier. So the first position will always start from 0, then 1, 2. So you see 1 into 2 to the power 4, 1 into 2 to the power 3, 0 into 2 to the power 2, 1 into 2 to the power 1, 0 into 2 to the power 0. So anything multiplied by 0 is 0. Let us go. 2 to the power 1 is 2, that is 1 into 2 is 2. 2 to the power 3 is 8, 1 into 8 is 8. 2 to the power 4 is 16, so 1 into 16 is 16. So 16 plus 8 plus 2 totals 26. So this is the binary number of the decimal value 20, decimal number 26. Octal number system. So earlier we have seen in decimal number system we have a total of how many digits? 10 digits. That is a base 10 and the numbers are 0 to 9. In binary number system it is a total of how many digits? 2 digits. A number system of 2 digits. What are those? 0 and 1. An octal number system, as you can guess by the name, is a number system of how many digits? 8 digits. That is from 0, if you count 0, from 0 to 7. Now, octal number system is also a positional value system. So, in the octal number system, the base is 8. In the binary number system, the base was 2. In the decimal number system, the base was 10. As the base is 8 in the octal number system, so the powers will be expressed as the powers of 8. As you can see here, 8 to the power 0, 0 for the first position, 2 to the power 1 for the second, 2 to the power 2 for the third, and so on. So now let us try to convert the decimal equivalent of an octal number. As I have said, the formula from any base to decimal number, the formula is the digit into base to the power position number. So let us go to the example. 726. It's 726 to the base 8. So it is an octal number. So in order to convert this octal number to the decimal number, we have to use the formula. So 7 into 8 plus 2 into 8 plus 6 into 8. Now we'll put the positional value. This 6, the position is 8 to the power 0. 2, the position is 8 to the power 1. 7, the position is 8 to the power 2. So 7 into 8 to the power 2, 2 into 8 to the power 1, 6 into 8 to the power 0. So 8 to the power 0, any number to the power 0 means 1. 6 into 1, the value will be 6. 8 to the power 1 means 8. 8 to the 16. 8 square means 64. 64 into 7 means 448. Once you total it, the number is 470. So the octal number of our normal decimal number system 470 is 726. Let us now talk about the last number system, that is hexadecimal number system. Now hexadecimal number system has total of 16 symbols. So first, ranging from 0 to 9, capital A to F, where A is equal to value 10, B is equal to value 11, and this number system is also, so all the positional values will be expressed as the power of 16. As you can see here, 16 to the power 0, to the power 1, 2. So let us go to an example to convert a hexadecimal number to a decimal number. So 27fa to the base 16. So f, the value of f is 15 and the value of a is 10. F is the last symbol of the hexadecimal number system. So let us convert 2 into 16 plus 7 into 16 plus f into 16 and a into 16. Now the value of f is 15, so we will write 15 in place of f. The value of a is 10, so we will write 10 in place of a. So the positional value of a is 16 to the power 0, positional value of f is 16 to the power 1, positional value of 7 is 16 to the power 2, positional value of 2 is 16 to the power 3. So after the calculation, we have got the number 10,234, or the hexadecimal number of the decimal number 10,234 is 27fa. Till now, we have seen how to convert all the other number system into our most common number system, that is decimal number system. Now we will go through how to convert a decimal number to other base system. So there are certain steps. Step 1. Divide the decimal number to be converted by the value of the new base. If I have to convert a decimal number to octal number system, then I have to divide that decimal number by base 8. Then we will get the remainder from step 1. So then again, after dividing the decimal number by the new base number, you will get the remainder and you will also get the quotient. So again, you have to divide the quotient by that base number, by the same base number. Again, you will get the remainder. Again, you will get a quotient. You have to keep on dividing until and unless you are unable to divide the quotient anymore. And you have to store all the remainders. Then we need to rearrange those remainders in the reverse order, and hence we will get the result. So we are considering here the example, the number 29. So we want to calculate a binary equivalent of the decimal number 29. So here are the steps. So first I have to divide 29 by 2. I will get the result 40. That is, the quotient is 40 and the remainder will be 1. Then again I will divide the quotient by 2. 14 by 2, 7. So the remainder I will get 0. Then again I have to divide this quotient by 2. 7 divided by 2. Remainder I will get. Again I have to divide 3 divided by 2. The quotient divided by 2. I will get the result 1 and the remainder I will get 1. So again I will divide. So now we will arrange in the reverse order, that is 1, 1, 1, 0 and 1. To the base 2 is the binary equivalent of the decimal number 29. So the remainders have to be arranged in the reverse order. So decimal number 29 is equal to binary number 11101 to the base 2. So in case of octal number, similarly you have to keep on dividing by 8. In case of hexadecimal number system, you have to keep on dividing by 16. So you see, in order to convert other base system to non-decimal system, there are some steps. First, we have to convert the original number to a decimal number. Then we have to convert that decimal number to the non-decimal system. So let us see for an example. I want to convert octal number 25 base 8 to a binary equivalent. We can convert a decimal number to any other system and any other system to decimal number. So we have gone through the steps. So now let us see. First 25. So we will be converting this octal number 25 into decimal number. So 25 2 into 8 plus 5 into 8. The positional value of 5 is 8 to the power 0. Positional value of 2 is 8 to the power 1. And we will get the value 21. So 21 is the decimal number or decimal equivalent of the octal number 25. So octal number 25 to the base 8 is equal to decimal number 21. So now we will convert this decimal number 21 into binary number or binary equivalent, and we will get the binary equivalent for the octal number 25. We have gone through the steps. We know we have to divide this number by 2. We have to keep on adding and then unless it is not divisible anymore. So 21 divided by 2, 10, remainder 1, 10 divided by 2, 5, remainder 0, 5 divided by 2, 2, remainder 1, 2 divided by 2, remainder is 0, 1 divided by 2, remainder is 1. So now we have to arrange it in the reverse order, 1, 0, 1, 0, 1. So the decimal number 21 is equivalent 1, 0, 1, 0, 1 base 2. So that means 21 decimal number is the equivalent of the octal number 25 base 8. So that means 10101 base 2, this binary number is the equivalent of octal number 25. Thank you.